So today's lesson is going to be on titration. So what is a titration? A titration is used to determine the concentration of a solution All right, and I've got this bracket here where a bracket means concentration, so it's just my way of abbreviating the word concentration. All right, so we're going to determine the concentration of a solution by using a solution that has a known concentration. All right, and SOLN, that's my abbreviation for solution. All right, so we can determine an unknown concentration by using a solution whose concentration that we do know. All right, a couple of other vocabulary terms. Equivalence point. This is where the mole of the acid will equal the mole of the base. And it's important to remember here, these values when we say equal are not necessarily the same number. So it's not necessarily 2 moles equals 2 moles because we know that acids can be diprotic or triprotic, and we know that bases can have more than one hydroxide, like calcium hydroxide, for example, has 2 hydroxides. So it is a stoichiometric relationship. All right, and we've already learned about an indicator in a different video. I briefly touched on it. We're going to talk about it again. An indicator is going to be very important in a titration because an indicator is going to be used to determine if our solutions are acidic or basic. And this is going to be based on a color change. All right, and the point at which that color changes is what we call the end point. All right, so point at which color change occurs is called the end point. All right, not to be confused with the equivalence point. The equivalence point is where the mole of acid equals the mole of the base. The goal of a titration is to choose an indicator where the end point and the equivalence point are very similar. And so the way we do that, there is a way to know that, and this is an extension. If you come see me in AP Chemistry, we'll talk about that and we'll learn how to pick indicators and whatnot. All right, so for the purposes of this class, I'll just give you the indicators that you're going to be using. All right, when we talk about a titration, we can take a strong acid, which I'm going to abbreviate strong acid SA. So if I have a strong acid, that means I have an initial pH that is less than 7. All right, so if this is my middle part of the pH scale, all right, I have a pH that's going to start at less than 7. If I add a strong base, we know acids and base neutralize. We're going to end up with a graph that looks like this, where the center of this line is what we call the equivalence point. All right. And when a strong acid and a strong base are added together, the equivalence point always has a pH of 7. If I start with a strong acid, so here I am again, and I add a weak base. So I'm going to abbreviate WB, W for weak, B for base. I still get a graph that looks like my strong acid, strong base. The difference here is the equivalence point, this center piece, is going to have a pH below 7. Now, again, there's a way to calculate this. We're not going to actually learn how to calculate this. This is an extension that we will learn in AP. If I start with a strong base, that means I have a pH above 7. All right, so I'm going to be at the top part of my pH. When I add a weak acid, my graph is going to look basically the same as my other two, except in the opposite direction. And my equivalence point is going to be above 7, a pH above 7. And there is a way to calculate that as well. We don't need to know that. So here's what we need to know. A strong acid with a strong base gives us an equivalence point of 7. A strong acid with a weak base gives us an equivalence point below 7. And a strong base with a weak acid gives us an equivalence point above 7. So let's do some practice problems. What volume of a 1 molar sodium hydroxide is required to neutralize 25 milliliters of 0.1 molar hydrobromic acid? Now, I'm going to give you a shortcut here, but I'm very hesitantly giving you this shortcut because students often use it incorrectly. So when I give you this shortcut, I need you to pay very close attention to when you use it. The molarity of the acid times the volume of the acid added equals the molarity of the base that is used times the volume of the base used. Here is where it is important. We can only use this if there is a 1-to-1 ratio, meaning that there is a monoprotic acid and a monobasic base, meaning 1 hydrogen lost for every 1 hydroxide. So 1 hydrogen ion for every 1 hydroxide. So in this case, hydrobromic acid is HBr and sodium hydroxide is NaOH. So I do have a single hydrogen and a single hydroxide. So in this case, I can use my shortcut. So what is the molarity of the hydrobromic acid? It is 0.11 molar. And the volume of the acid is 25 milliliters. The molarity of the base is 0.1 molar. And we are solving for the volume of the base needed. So when we solve for this problem and we plug this into our calculator, we get a value of 27.5 milliliters. Now you can, because we have volume on both sides, you can use milliliters or liters, because essentially if I divide both sides by milliliters, units cancel. If I divide both sides by liters, units cancel. But this can only be used in a 1-to-1 ratio. So let's look at another example. I have hydrochloric acid and barium hydroxide. I know my formula for barium hydroxide is BaOH2. So I have 2 hydroxides for every 1 hydrogen. So in this case, I'm going to have to write out a balanced equation where hydrochloric acid plus my barium hydroxide will form a salt and water. So in this case, it will be barium chloride and water. And then I'm going to have to balance my equation, and that should be BaCl2. All right, and so when I balance my equation, I notice I need 2 and a 2 there. All right, so now I'm going to have to do a Rebecca chart. If you're not sure how to do a Rebecca chart, you need to go back and watch my video on Rebecca charts. Okay, so to find this, what am I going to do? I know the volume of the acid, I know the volume of the base, and I know the molarity of the acid. So I'm going to start by finding the moles of my acid here. So 1 molar is my moles over the liters, which is 0.0354 liters. So that's going to give me 0.0354 moles of hydrogen. All right, and so I need to figure out how many moles of hydroxide are used. Now remember, this is a stoichiometric relation here. All right, so it's going to take 2 moles of hydrochloric acid for every 1 mole of barium hydroxide because of this value of our hydroxide here. So I'm going to have a 1-to-2 relationship times 0.0354, and that's going to fill in my Rebecca chart with a value of 0.0177. So for every 0.0354 moles of hydrochloric acid used, I will have 0.0177 moles of barium hydroxide. All right, and now we are here at our equivalence point, because when we solve our hydrochloric acid, we notice that both of these are used up. Both the acid and the base are used up. So what is the concentration of the base? It took 67.3 milliliters, and I had 0.0177, so 0.0177 moles of hydroxide for every, or for a value of 0.0673. Okay, 0.0673 liters. So that means that I had a concentration of base of 0.263 molar. Let's do us another problem. All right, I have a solution of potassium hydroxide, that's KOH, with a concentration of 0.298. 133.73 mils of potassium hydroxide are needed to exactly neutralize 50 mils of sulfuric acid. Sulfuric acid is H2SO4. All right, so we want the concentration of the acid. Now, what do I notice here? I notice that I have 2 hydrogens for every 1 hydroxide. This is not a 1-to-1 ratio, so again, I'm going to have to write myself a balanced equation. I have potassium hydroxide plus sulfuric acid, and that is going to neutralize to form a salt and a water. So K2SO4 plus H2O, and then I simply have to balance my equation here. All right, so when I set up my Rebecca chart, I want to try and find the moles of acid required. I have the information to find the moles of base that was used, all right, because I have the molarity and the volume. So 0.298 molar equals moles over 0.13373 liters. So that's going to give me a value of potassium hydroxide in terms of its moles of 0.0399. All right, so now how many moles of high sulfuric acid are needed? All right, it is a 1-to-2 ratio, which is going to give me a value of 0.01995. And if we were to solve for our potassium hydroxide, now I'm going through this Rebecca chart really quickly because it's my assumption that you know how to do a Rebecca chart, because this is a previous topic, so go watch that video if you need to on the Rebecca chart. We are at equivalence point because my acid and my base have been completely neutralized. All right, so what was the concentration of the acid? It took 50 milliliters of acid, and it took 0.01995 moles of acid, so that'd be 0.05 liters. So we find that we have a concentration of 0.399 molar sulfuric acid. All right, so let's calculate a couple of things and then let's graph these. All right. This is like a lab that we're going to do. Let's say that you started with 20 milliliters of 0.06 molar hydroiodic acid, and you had lithium hydroxide that was 0.02 molar. So what is the initial pH? Before I add any base, I notice this is a strong acid. Strong acids are going to go to completion. So all I have to do here is take the negative log of the H3O plus, and since this is going to create all H3O plus, my concentration of 0.06 is what I plug in. So the negative log of 0.06 gives me a pH of 1.22. Now, let's say I had this solution and I added lithium hydroxide. So that's where I am right here, part B. I am now adding 30 milliliters of lithium hydroxide. Lithium hydroxide is a strong base, so I'm going to produce all hydroxide ions. So my net ionic equation here is the hydrogen plus the hydroxide will give me water. Iodide and lithium are spectator ions. They are not involved in this process. We do not need to include them. So how many moles of hydroiodic acid did I start with? All right. So step one, I take the molarity of my hydroiodic acid, and I can find the moles that I started with, which 0.02 liters. So that's going to give me a value of 0.0012 moles of hydrogen. So this is my value that I plug into my Rebecca chart. All right, this is a 1-to-1 ratio here. Yes. Now, I've got to figure out my amount of hydroxide that I've added. So my hydroxide had a concentration of 0.02, and I've added 30 milliliters. So that's going to be a value of 6 times 10 to the minus 4th moles of OH. So this is my value for my hydroxide. Now, this is a 1-to-1 as we noticed. So because this is a 1-to-1, my smaller number, the hydroxide here, is what's getting used up. So that is what is the limiting reactant in this reaction. So I'm going to have 6 times 10 to the minus 4 hydrogen afterwards. But this is important to remember. I have literally mixed two things together. I mixed 20 milliliters of acid and 30 milliliters of lithium hydroxide. So my final volume is 50. So I have a solution of 50 milliliters, and in that solution, there are 6.4 times 10 to the negative 4th, or 6 times 10 to the negative 4th moles of acid in my solution. That is 50 milliliters. 20 plus 30 is 50. So 50 milliliters is 0.05 liters. So the new concentration of hydronium ions is 0.012. This is a hydrogen that is in excess. So when I take the negative log of a hydrogen, that gives me my pH, which is going to have a new pH of 1.92. All right, let's say I had 60 total. Okay, so we'll pretend like I haven't added the 30. I'm at the 20, the 0.06 and the 20, and now my total volume I add is 60. So this is another problem, okay? So let us start here with our H plus and our OH minus is going to give us water. Now we've already in part B calculated the amount of hydrogen. All right, that's not changing in part B. So I'm just going to go ahead and carry that down. You only need to show your calculation one time. But my acid is not changing, my base is. So I added 60 milliliters of 0.02 molar base. So that's going to be 0.06, and that's going to give me a value of 0.0012 moles of hydroxide. So I'm going to take this value and put it in over here. What do I notice? I notice I have an acid and a base in a 1-to-1 ratio, and their values are the same. So they will both be used up. They're used up completely. So now I'm at what we call the equivalence point, where the mole of the acid equals the mole of the base. And since it's a 1-to-1 ratio, these values are the same. I have a strong base and I have a strong acid. So a strong base and a strong acid at equivalence point will always have a pH of 7. All right, let's calculate it at the addition of 90 milliliters. All right, so I've already calculated my hydrogen ion. So again, we're now pretending like we didn't do A or B. What if I started with 20 mils of 0.06 acid and I added 90 mils of 0.02 base? All right, we've already calculated how many moles of acid there are in our original acid, but what about our base? Our base is changing. The concentration is still 0.02, but in this case, I am now adding 90 milliliters, which is 0.09 liters, 0.09, let me make that look more like 0.09 liters. All right, so when I solve for the moles here, I'm finding that I have 0.0018 moles of hydroxide. So this value goes into my Rebecca chart. Now, again, it's a 1-to-1 ratio. 0.0012 is the smaller value, so this is my limiting reactant. This is what's going to get used up, causing this completion of the reaction. All right, so when I subtract that out, I find that I have 6 times 10 to the negative 4th moles of hydroxide. Hydroxide is now in excess, so this is going to be a basic solution. Now, in this case, what did I do? In this case, I took 90 milliliters of base and I added 20 milliliters of acid together. So I have a total here 110 milliliters total in that solution. So I have a solution that has 6 times 10 to the negative 4 moles of base and a volume of 110 milliliters, which is 0.110 liters. So that gives me a concentration of base of concentration of OH of 0.00545. So this is a OH coming from the OH. So when I negative log the OH 0.00545, that gives me the POH. So the POH, when I take the negative log, is going to be 2.26. So I'm going to have to take 14 minus 2.26 to get the pH, which I find to be 11.74. Now, it tells you to graph your data. So let me show you my graphed data. All right, let's look at this. What do we notice here? We notice that when we graph these points on our data, we do get this sharp curve, and we go all the way here. This is my equivalence point. My equivalence point is halfway in between where that line becomes that straight line. All right, and when 60 milliliters of volume of base was added, we did have a pH of 7, where we had the equal number of moles of acid and base. Quick review. Remember, it is a stoichiometric relationship. All right, so back here on these previous problems, we had twice as much acid as we did base. We had twice as much base as we did acid. All right, but we are still at equivalence point the moles of acid equal the moles of base because it is a stoichiometric relationship. These numbers do not necessarily have to be the same. It is based on this Rebecca chart and our stoichiometry. Please be careful.